Okay, everybody, thanks for joining us again today. We have a special guest I think you'll really enjoy, Dr. Mark Jackson, who works for Cambridge Quantum Computing. He and I met each other a few years ago, and he's agreed to come on and tell us a little bit about where the state of quantum computing sits and what is happening in this crazy world of quantum computing that is just starting to open up. So let me start out by letting Mark explain to us a little bit about what he's been doing over the past few years as he got into this business. I know your degree is in quantum computing, so maybe you could give us a little bit of background on that as well, Mark.
Sure thing. So thank you, Marv, and thank you, Jim, for having me on your show. Um, so yes, I'm the quantum evangelist at Cambridge Quantum Computing, and it's really an incredible time. It's historic. I think there's no other word for it. This will be a time that they talk about hundreds of years from now, because this is really the first time that we've made an advancement in how we store and we process and we calculate. Um, when I give presentations about quantum computing, I often point out that computers, as we know it, were invented about 200 years ago. And even though they look simplistic, it's actually still the basic ideas of our computers today, like the laptop that sits in front of me. Quantum computing is the first advance in that. And so that's why it's so exciting. We can talk about that a little bit later, but since you asked about my background, so yes, my degree is in quantum physics. So I got my PhD in string theory at Columbia University in New York, and for many years I was in academia doing research in string theory and cosmology, and so I did things like the Big Bang and black holes and grand unified theories and such. And I left that briefly to do my own startup, and then I briefly returned to academia. And this was about 5 years ago. I started hearing about quantum computing. And of course, this didn't exist commercially when I was a student. And so it was really interesting to me to hear that there were now these computers being built. And I wanted to kind of get into this, but because I didn't have a background specifically in that, and I didn't really know of anyone, I sort of felt sidelined. I felt like I was kind of a cheerleader. I would sometimes give presentations about it to public audiences, but I felt like I was missing out because I knew this would be an important field. And I was very lucky about 4.5 years ago to have dinner with a friend of mine in Berkeley. He's a math professor there. And he offered to introduce me to Ilyas Khan, who was the founder and CEO of Cambridge Quantum. And it was very well timed because they were about 3 years old, and they were based in the UK, of course, and they were looking to expand into the US. And so I was the first hire in the US. And so it's been about 4 years that I've been there, and it's been quite a ride.
That's excellent. Well, how about just giving us a little bit of foundation on what is quantum computing? I'm sure we'll have people in the audience that don't track it as much as Jim and I have, and even then, I can't be an expert on it like you are in any sense.
Sure. So first, let's review what normal computers are, and then I can explain how quantum computers are different. So normal computers, recall, use bits, binary digits, right? So bits are just ones and zeros. Everything on a computer at the most basic level are ones and zeros, which are like little on-off switches, right? So it's on or it's off. There's nothing in between. A quantum computer can be in between a zero and a one, and that sounds a little strange, but I often think of it like a coin. A bit is sort of like a coin sitting on a table. It's heads or it's tails. It's one or the other. But a quantum bit, or qubit as we call it, is like a coin spinning in space. So you kind of arbitrarily angle it any way that you want. It could happen to be heads, like purely heads, or purely tails, but there's a lot in between. And funny enough, the reason that's a really good analogy is that's actually mathematically identical to how these qubits work. If you actually think of a vector or an arrow pointing in space, like a coin would, depending on which face it's facing, um, that's mathematically identical to how a qubit works. And so quantum computers use these qubits to do calculations. And you might ask, well, why is that so important? Why do we go to all this trouble of having quantum bits and things like that? The reason that that's so important is because a quantum bit can do two things at once. It's considering the zero case and the one case simultaneously. And the technical name for that is superposition. So we say that this qubit is in a superposition of the zero state and the one state. and it's weighted differently in general, right? So it might be like 10% for the 0 case and 90% for the 1 case. And there's even a more subtle feature called the quantum phase. But the point is that these qubits can represent several different configurations at once. 1 qubit represents 2 configurations at once. 2 qubits represents 4 configurations at once. 3 qubits represents 8 configurations at once, and so forth. So every time you add a qubit, you're doubling the number of configurations that you can consider. So 30 qubits corresponds to about 1 billion different combinations. And again, that's all handled simultaneously. And not every problem can take advantage of this. So that it's actually only very specific problems that can do calculations in this way. But if it can do calculations in this way, it can be much, much faster than a normal computer. In fact, it's so much faster that we think quantum computers could solve problems that we never could have hoped to have solved with normal computers. So it's not just a faster computer, it's so much more powerful for some problems that we should be able to solve problems that we never could have hoped to have solved before.
So, Mark, I know that Cambridge Quantum Computing is not really being in the business of building quantum computers, as there are several companies around the world doing that. Explain to us a little bit about what they really do and why it's so important.
Sure. So Cambridge Quantum focuses on the software of quantum computers. So just like with normal computers, there's hardware and there's software, and we have focused on every area of the quantum software package. So we have developed our own compiler, which is hardware agnostic. So that means that you can use your favorite quantum programming language to write a program and execute it on your favorite quantum hardware. So the compiler does the translation and it finds the most efficient way to run the program on your favorite quantum computer. We have machine learning, and we have chemistry, and we have natural language processing, as well as cybersecurity. And so we've been developing software in all these areas. There are many groups building hardware for quantum computers. So there's big corporations like Honeywell and IBM and Google. There are startups like IonQ and Rigetti. There are many academic groups. So there's lots of groups doing this. There are a lot of technical approaches to building a quantum computer. So there's not just one way to build a quantum computer. There's many different ways. Some of the more popular ways include superconducting quantum computers. And you might have seen these pictures. They sort of look like chandeliers with wires hanging down, and they get lowered into a cryogenic chamber. So this refrigerator that's kept at near absolute zero. There's the ion trap method, in which you manipulate these charged particles, ions, using lasers. There's photonic, where you're actually using individual photons, usually on a chip, to do the calculations. So there's lots of different ways to do this, and they each have their own advantages and disadvantages. And I truly don't know who the winner will be. There will probably be a few winners. We've seen extraordinary progress. It's been much faster than Moore's law, the rate of progress in quantum hardware. Just in the 4 years since I've been in the business, we've seen incredible progress. And both IBM and Google predict that they will have 1,000 qubits within 2 or 3 years, and they think they will have 1 million qubits within 10 years. And so that really will be incredible. We think that we're about 3 to 5 years away from being able to commercially deploy quantum computers. So that's how close we are.
Yeah, Mark, I know on the software side, like the new hot thing is kind of go the open source route, where you build an open source community. Is that kind of what's happening in the software side of
it is. That's actually a very well-timed question, because there's a nonprofit group called the Unitary Fund, which awards many grants in open source projects. And the compiler that we've developed, we call it Ticket. We are moving towards not necessarily open source, but right now it's open license. So everyone can use it free of charge. There's no issues with licensing or permissions or anything. The only thing that we ask is that you give us feedback on how we can make it better. And if you write an article using Ticket, that you just credit us in the article. But as time goes by, we might be moving in the direction of open sourcing that. Yes.
You may have heard the Marine Corps just fly overhead in their F-18 jets. So, Mark, I know that part of the problem with quantum computers is they have a large noise component, and it's hard to control that noise and continue the entanglement between whatever the source is, right? The photons, et cetera. So where do you think these quantum computers are relative to useful maturity? I mean, when are we really going to do something like a chemistry or physics problem like you're looking at?
Sure, sure. So just to clarify for the audience, when we talk about noise in quantum computers, we don't literally mean that they make a lot of noise. So when we say noise, we mean that they have a large error rate, and that means the qubits don't do what we want them to do. So this could be the qubits change their answer for no apparent reason. Sometimes they interfere with other qubits in a way that we don't want them to. Sometimes we do a measurement and we don't actually measure the answer that we thought we were going to get. So qubits have a lot of sources of noise, and we parameterize all these different types, and we take this into account. And yes, Marv, you're exactly right. Right now, quantum computers are still too noisy, and that means that it's still too likely that they'll make a mistake. Many people probably aren't aware that normal computers, when they have bits, they do have noise. There is a chance that a bit will make a mistake. It's not often, but it's very easy to correct with normal computers. And the way that we correct it is we just make triplicate copies of bits. So instead of using 1 bit to store some information, we use 3 bits to do that. And so in the unlikely case that 1 bit flips and makes a mistake, the other 2 will indicate, well, the answer is supposed to be that, right? If we just agreed to take the majority, then it's very obvious which bit was wrong. And so assuming that it's very unlikely a bit will make a mistake, we can get away with just triplicating it. So you might ask, well, why can't we just do that with quantum computers and play the same game of error correction, it's called? And the problem is that quantum physics has some rules, which are a bit funny. And the rules are that you can't copy quantum information. You can move it around, but you can't copy it exactly. And the other rule is that once you measure something, you've destroyed some of the information. And so just the act of measuring it itself disturbs it. And so at first blush, it might seem impossible to even do error correction with quantum computers because we can't make copies of it and we can't even measure it to see what might have gone wrong. And so you could be forgiven for thinking that it would be impossible to do error correction. Fortunately, a very smart person, a professor at MIT named Peter Shor, he developed a way to do quantum error correction. And so now we have all sorts of sophisticated ways of doing this. What you do is you actually spread the information on 1 qubit among several qubits. And it's a complicated mathematical way of doing this, but by spreading out this information, there's actually clever ways that you can measure the other qubits to identify a source of error and then correct it, all while leaving the original qubit alone. So it's kind of funny that there's this loophole. You can measure the other qubits, the auxiliary qubits, but leave your qubit alone. And in this way, you can cleverly correct for any errors that pop in. And so this is what we plan to do with quantum computers. We're not quite doing it yet because for this to work, the noise has to actually be below a certain threshold. And the reason for this is because if qubits are too likely to make a mistake, adding more qubits actually makes the problem worse. Even though you're trying to improve it by spreading it out among many qubits, if the error rate is too high to begin with, you're actually making the problem worse. And so we have to wait a little bit longer to bring the error rate down a little bit before we can start doing error correction. To answer your question about the time scale, we think that it's only 3 to 5 years before we might start to see commercial deployments. And that's not far off at all. It takes time to develop quantum applications. We're usually starting from scratch. So the projects we're working on now take 1 to 2 years to develop. And so that's why companies are starting to invest now so that they'll be in a good position to take advantage of this in a few years. They're kind of developing their quantum muscle, so to speak. They're becoming familiar with quantum computing and learning how this will affect their field and how they can get involved in it. And they're taking the first steps to developing the programs so that they can take advantage of it in a few years.
Yeah, Mark, that noise that you talked about, is I used to use like decoherence or the lack of coherence. Is that still kind of the main issue, or?
It is that's the issue. That's the reason that quantum computers work. That's kind of the secret sauce, is because when I described a qubit as being as in the 0 state and the 1 state simultaneously, this superposition, that's possible because of coherence. And so when we say that a qubit, a quantum state or a qubit still has coherence, it means that it's preserving that superposition, right? When we say a qubit loses its coherence, it means that the state has chosen one of those configurations. And it, at the very end of the program, when we do our measurement, we're done, we want it to lose coherence, right? We're measuring it and we're done, but we don't want it to lose coherence until then, because if that happens, then all the special properties of quantum computing go away, and it just becomes like a normal computer. And so yes, it's preserving this coherence. That's really the tricky part. Yeah.
And is that getting solved by different techniques, and like I think of clusters or nodes, or multiple nodes type mentality?
It is. So these different approaches that people are using for quantum computers. So those are all focused on how we can preserve coherence as long as possible. And so the different techniques have different trade-offs. So for example, superconducting quantum computers, the advantage is that we've been using superconducting technology for decades. So we have some experience with that. The operations are very fast. So we can do calculations in nanoseconds, like billionths of a second. The disadvantage is that the coherence doesn't last very long. It's on the order of milliseconds, right? Ion trap technique, it's a little bit newer. The advantage is that you can do it at room temperature. You don't need to have all this special equipment to keep it near absolute zero. The coherence time is much, much longer, on the order of minutes. So you can actually retain these special quantum properties for a long, long time. The disadvantage is that the operations are slower. And it's actually funny, it's about the relative scale of operations to coherence time is actually about the same. It's about 1,000 times, the coherence time is about 1,000 times of the operation time. So just by a funny coincidence, the trade-off is the same. But yes, so trying to get these qubits to stay coherent as long as possible is really the fundamental challenge.
So Mark, given that measurement in quantum physics causes disruptions or loss of information, how do you get an answer out of a quantum computer?
You do want to make the measurement eventually, but only at the end of the day, when your program is done running, then you can do you do the measurements on the qubits and you get some answers. And so as I mentioned, every quantum program has 3 basic steps. So the first step is the initialization. So you initialize all your qubits. It's usually to the 0 configuration. There are exceptions, but usually we start the qubits in the 0 configuration. And then we do operations or manipulations. So we do procedures, and we have the qubits do things. Sometimes we do them to qubits by themselves, and sometimes the qubits are interacting with each other. So they change their values around. And then at the end, we do the measurement. So every quantum program has those 3 steps: initialization, operations, and then the measurement. We need to keep the coherence during those operations, right? Otherwise, the special quantum properties are lost, and there's no point to doing this. And so yes, this is what we do. At the very end, the qubits are in this superposition. So the qubits they're representing several different configurations. When we do the measurement, we're forcing the qubits to choose. So when we do a measurement on a qubit, we're forcing it to choose, are you a 0 or are you a 1? And it will make a decision. So we don't ever get to see the qubit exist in these multiple configurations. I know it seems very science fiction-y when we describe all these simultaneous configurations. And mathematically, that is what's happening. But when we actually do a measurement, we only ever see one possibility. And so we actually don't know what the outcome will be for certain. We only know the probabilities of how it's going to come out. And that's actually a big difference with quantum computers compared to normal computers. With a normal computer, if you run the same program again, you should expect the same answer. Unless the computer is physically broken, if you have the same input and you run this program again, you should get the same output. With a quantum computer, you could get different output each time you run it, and nothing is broken. That's just how quantum physics works. You do the same operations and manipulations, and then you do the measurement, and you could get different results. And so that's why we often run the program many times. It's usually like 1,000 times. So we get a histogram of what the results are like, how likely we are to get each outcome. And usually that's the important quantity that we're going to use.
So can we put this into a practical discussion? Let's say you're trying to do a material science breakthrough on some new kind of a molecular structure, or even a chemical one where you're trying to find a new chemistry that might help some problem. How does this application of quantum computers really solve something like that?
Yeah, so that's actually that was the first example. This is actually why quantum computers were first thought of. About 40 years ago, Richard Feynman, the famous physicist, he was thinking about these types of problems like chemistry. And he realized that there were a lot of problems that we would never be able to solve using normal computers. And that sounds funny. Like, don't we use computers to do chemistry and science all the time? We do, but there's a limit. When you have a molecule, the larger the molecule gets, the more atoms there are, and each atom has electrons. And so as the molecule gets bigger, we're considering more and more electrons. And we know what the equations are for simulating molecules. We've known for 100 years. The equations by themselves aren't difficult. But as the molecule gets bigger and we have more electrons and more protons in the center, every interaction there has an equation, right? And so solving all those equations simultaneously becomes very difficult for a normal computer to solve. And this is why we can simulate only the very simplest molecules using classical computers. And Feynman realized this. He saw that this was an example of a much broader class of problems, that as you make the problem a little bit more difficult, as you make the molecule a little bit bigger in this case, it becomes much more difficult to solve. And so he realized that normal computers would never be able to solve this. And we needed to develop a new type of calculator based on quantum physics, because these equations are quantum type equations. And so he suggested we build these things like quantum computers. But of course, 40 years ago, we didn't really know how to do that. And so a lot of academic research was done. And the joke was that quantum computers were always 10 years away. And that was true for about 35 years. But about 7 years ago, there were some breakthroughs that people realized that this might be commercially feasible. We might be able to actually build them and have it be worthwhile to do certain problems.
Yeah,
So,
very similar to directed energy. Right.
Yes. So that's how it works. Yeah, we know what the equations are for chemistry, and we can use normal computers to solve very simple cases, but large molecules we would never be able to do. So for example, caffeine, my favorite molecule, we would need a computer about 1/10 the size of the Earth to simulate that. And so that's clearly not very practical. And if we wanted to do a molecule about twice as big, like penicillin or something, we would need a computer about the size of the universe. So even theoretically, you couldn't get anything bigger than that, but a quantum computer could do that pretty efficiently. So for example, the second molecule I mentioned, we would need a quantum computer with only about 300 qubits. And so that's not impossible. We can't do it today, but that's not at all impossible. And so that's why we're so excited. When I talked about being able to solve problems that we never could have hoped to have solved before, that's a prime example.
So Mark, let's cut over for a second to cybersecurity, because we've all heard that our encryption algorithms are going to be in jeopardy when these quantum computers can actually break down the mathematic structure of the random numbers. Where are we with that, and what can be done about all that?
Sure. Yeah, this is, I get asked this a lot, because if there's one thing that people might have seen, it's that they've seen headlines about quantum computers and hacking and threats and such. And so first, let me explain why that is and the truth in that. So when you transmit information on the internet, you're usually sending some sort of encrypted version of your information. So like when you type your credit card numbers in to do some online purchase, what happens is that your computer encrypts those credit card numbers. So it applies a complicated mathematical formula, and that's what's transmitted. And then the computer on the other side will decrypt it. So it applies some inverse mathematical formula to undo it, and they get your credit card number safely.
Yeah.
If someone eavesdrops and they intercept that communication, they'll just see gibberish. They won't actually see your credit card numbers. And the mathematical formulas that are chosen to do this are purposely so complicated that it's very difficult to directly undo that formula unless you had a key, right? When you hear about hacking nowadays, it's usually not because someone directly undid the formula. It's because of some human error, like they bribed someone to undo it, or someone wrote their password down on a sticky pad or something like that. It's usually not that they directly undid the mathematical formula. So when these formulas were developed several decades ago, they were chosen to be complicated enough that normal computers would never be able to undo them directly. Quantum computers, it turns out, are good at undoing them. And of course, they didn't realize this at the time because quantum computers didn't exist. About 25 years ago, this same professor at MIT, Peter Shor, he developed a formula, an algorithm for how quantum computers could efficiently undo it. And this was academically interesting that this existed, but no one took it very seriously because there were no quantum computers. Now that quantum computers are becoming kind of powerful, people are starting to worry. It won't happen tomorrow, but at some point in a few years, it might be that quantum computers could directly undo the encryption formulas that we often use. So RSA is the usual example that people give. There's other examples too. So what can we do about this? So the good news is that, of course, people have been aware of this for several years. And so many people have been developing alternative encryption formulas based on mathematics that we don't think quantum computers could undo. And I want to underline that we don't think. We actually don't know for certain. That the government agency NIST in Colorado, they sponsored a contest for people to submit what are called post-quantum encryption algorithms. And a few years ago, the initial submissions came in and there were over 100. And that people then did their best to defeat these. So using mathematics and computer science, people tested whether they could have a quantum computer defeat them. And so several were found to be vulnerable. There are now 7 finalists. And we think in the next few years, NIST will announce 1 or 2 winners. So 1 or 2 will probably emerge as being secure, that we don't think quantum computers could defeat them. And so yeah, that's the good news, is that people are very aware of this. They're already developing defenses against quantum computing. And if you're in a position to upgrade your system's security, I would encourage you to do it now. Some people are tempted to wait. Like they think, well, what's the threat? I'll just wait until I start to hear about quantum computers being more powerful. I wouldn't wait until you see headlines of this actually happening, because it takes time to do this upgrade. If you're in charge of a government agency or a large corporation, of course, there's a lot of legacy systems. It can be complicated. It can take months or even years to do that upgrade. So I would start now. The second reason I wouldn't wait is because there are rumors that hostile bad actors are archiving things right now. And so when their quantum computers become powerful enough, they will just be able to decrypt it. So this kind of harvest now, decrypt later attitude. And that would still be bad. If someone got a hold of your health records or your bank statements today, it would still be bad news if they decrypted it a few years from now. And so that's why I would strongly encourage people to start upgrading right now.
So Mark, I know you guys out there were at one point in time working on entangled photon quantum random number generators, which would be a different take on this problem, correct? It would
That's
produce
right.
a true random number that would not be breakable by a regular computer or maybe a quantum computer. Can you tell us where that is and what's going on with that?
Sure. So whatever encryption system you're using, whether it's the old type or the new post-quantum type encryption algorithms, you need random numbers. And so these numbers are used for the keys to encrypt or decrypt whatever you're doing. And this is often overlooked. People just take for granted that random numbers are easy to come by. I don't know, they ask their computer for random numbers or something. They don't give much thought to the fact that it's actually very difficult to come up with a truly random and secure random number. And the reason that this is subtle is because when you ask your computer for a random number, a normal computer can't do anything random. It just follows instructions. What it does is it produces a pseudo-random number. So it has some formula
Right.
which uses soft settings, like internal settings, like the number of milliseconds since you turned your computer on or something. And it uses a formula to produce numbers which look random to us casually, but they're not. It's a formula and it can be predicted and it can be intercepted. And so, so that's not secure or random at all. Using quantum physics, you can produce random numbers. So for example, when I talked about qubits being the superposition, if you set up a qubit so that it was half in the 0 configuration and half in the 1 configuration, and then you measured it, it's a 50-50 chance whether you'll get a 0 or a 1. And so by doing that repeatedly, you could get a random set of bits, and you could turn that into a key. So that's good, but if you do that, there's no way of knowing whether someone is tampering with it or eavesdropping, right? If you just get a string of bits, even if it were random, you would have no idea whether that's true or not, right? There's no security. There is a way to do this. So quantum physics also has another trick up its sleeve called entanglement. And entanglement is when the value of one qubit is correlated with the value of another qubit. And this is a purely quantum effect. There's no classical version of entanglement. And what you can do is you can produce an entangled pair of qubits, and you can then measure them independently. And as long as they were entangled, you should get identical results because of that, right? And so then you can just check whether you're indeed getting the same results. And if you are 100% of the time, then you can feel confident that the number truly is random and it's secure. Because if anyone had tried to tamper or eavesdrop or something, they would break the entanglement before you, and you aren't guaranteed to be getting the same answer every time.
Is that
And
like
so,
a modern version of a public and private key in some
it's a bit like that, yes. And so so there's this very clever technique using quantum entanglement where you can not only produce random numbers, you can prove that they're random and that no one knows what they are except you, that you got there first. And so that's really what you need for generating keys. You need to have them random and you need them secure. And the only way to do that is using quantum entanglement. And this is something that CQC has been working on for a few years. And we developed a way of doing this using quantum computers. And so, so there's now a service on IBM's quantum computer cloud where you can use their quantum computer to generate these provably secure keys.
So Mark, this is such a fascinating discussion. We're already into our 30-minute normal timelines. Let me just ask you one last area to get off the stage probably, and then I'd very much like to continue this on with another session.
Sure.
But when you're talking about the entangled communications, it reminds me about the satellite entanglement that the Chinese accomplished not too long ago, where they entangled the communication between Earth and the satellite, which is a phenomenal accomplishment. So I know the Chinese are competing with us for almost anything you can think of, AI and quantum for starters. What's the status of where we are with things like that, and what's going on between China and the rest of the world in quantum computing?
Yes, so you're absolutely right. The same entanglement that lets you produce these provably secure keys, it also lets you have provably secure communication, because if anyone intercepts that entanglement, intercepts the communication, it would break the entanglement, and you can detect that. And so this type of communication is called quantum key distribution. And it's usually only used to transmit keys securely, because for reasons I'll explain, there's a lot of overhead and it's kind of slow. And so we usually don't use it to send the communication itself. We use it to securely send the keys, and then we set up a secure communication on normal digital channels. So the Chinese did send up a satellite called the Messius satellite, which does this using lasers, and it has entangled photons between space and the Earth. And so this is an incredible accomplishment. There is sort of an arms race in the quantum technologies area between the East and the West. And China is very aggressively pursuing quantum technologies, especially communication. This is really their wheelhouse, is setting up things like this. We know that they're outspending us at least 11 to 1, and that's just what we're aware of. They're probably spending more that we're not even aware of. The US has started to focus on this a little bit more. They've given money to national labs now. A lot of universities have set up programs. We have several corporations. I mentioned like Honeywell, IBM, Google, all have great programs. And Europe has a lot of programs. Obviously, we're a British-based company. Germany is getting into it a lot. The Netherlands has a very strong program. And so, so there are efforts, but China is very single-mindedly getting into this. And of course, there's a much closer connection between industry and the government there, and the military. And so they're basically just writing blank checks to fund quantum development.
Fascinating. I just want to ask you one more question. You reminded me of the AI arms race we have going on with China. So is there anything particular about artificial intelligence that quantum is going to radically improve for us?
It's yes, there is a relationship there because AI really depends on machine learning, and quantum machine learning, we believe, will have several advantages. So one is in Monte Carlo simulation. So a lot of things when you're simulating some sort of random process, we use Monte Carlo simulations. In natural language processing, there's actually a very nice connection between the mathematics of natural language processing, like how we communicate using normal words, and then how things like Alexa and Siri understand them. There's a very nice connection between the mathematical structure of that and quantum computing. And we actually hired a prominent professor at Oxford, Bob Cook, who's the world leader in quantum natural language processing. And so I think the next 2 years, we'll see a big development in quantum AI from these types of things.
Yeah, Mark, I have kind of a people question. So I think recently I heard on a podcast, like most of the programmers in Silicon Valley are leaving kind of the IT community to move over to distributed finance and blockchain and, this whole crypto crazy market. What's it take a programmer today who wants to get into quantum computing from a software point of view? Does he have to relearn a new language, or, do we have enough people to support this idea of going after and doing quantum computing?
Yeah, that's an excellent question. And I'm in a good position to answer, I think, because I had to make this transition, and so I can attest to what it took. So even though I have a physics PhD and I spent several years doing research, I don't even do the research in quantum computing. I'm on the business side of the company, and that's because it's not like you can just quickly go to a boot camp, learn a few things, and then start writing quantum algorithms. There's actually a lot of things that you have to learn. There's a lot of background knowledge. And so the people that we hire to do the research tend to have degrees in specializing in quantum computing, or something very similar, and then they can catch up. So when I started about 4 years ago, there were maybe 10 serious startups in quantum computing. Now there's hundreds. I don't even know what they are because there's a new one that pops up each week. But yeah, there's such a demand now for needing people in this. We are starting to see a lot more universities have programs in quantum information sciences. That's the academic term for this. So they now offer degrees in this. There are online courses. I think MIT X Pro is one. There's sort of some online certification. I think IBM, they call it QuizKit. That's the name of their language. They offer an online course and certification. So there's a lot of ways that you can do this, but it does take some investment in your time to do this. You do have to learn about quantum physics and how this works. It's so counterintuitive compared to programming a normal computer. We just take for granted that computers actually think a lot like us. Quantum computers, it's just crazy. It's really not at all intuitive to develop these things. Yeah.
Thank you.
So Mark, this has been a fascinating discussion. I really thank you for coming on and giving us all of this information, and we definitely want to get back and carry it a little bit further and talk about it. We can actually hear the AI people talking about the day when the AI writes the quantum equations
Yes.
or algorithms. So let me thank you, and we'll get off the stage and give you back the rest of your day.
Super. Thank you. Thank you both.